All right, so now that we know how to take derivatives of exponential functions, we kind of revisit all the applications that we've done in the past with all of our other derivatives. We can find relative extrema. We can find absolute extrema. We can have situations where we might need the product rule or a quotient rule, and obviously chain rule. We also have things where we're finding rates of change or intervals where a function is increasing or decreasing, okay? All of those things apply here still. We just have a new function that we're able to do this with, okay? So let's take a look at this function here. We want to find the relative extrema of f of x equals x times e to the x. All right? We have a really small function there. Let's write it a little bigger. F of x equals x e to the x. Now, if I'm finding relative extrema, what do? What's our process for doing that? Take the derivative, okay? And set it equal to 0, yeah, okay? So we've got to find f of f prime equals to 0. Now, how am I going to find the derivative of x e to the x? It is a product rule, okay? It is product rule. We have two functions multiplied together. So u prime v plus uv prime, the derivative of the first, which is 1 times the second, plus the first times the derivative of the second. What's the derivative of e to the x? Same thing, e to the x. Okay? So, now we have to set that equal to 0. Okay, how are we solving that? Factor? Okay, so I see an e to the x they have in common. When does e to the x equal 0?
Never.
Wait, what is it? Never. What's the range of the exponential function?
Greater than 0.
Anything greater than 0. Remember, we have that asymptote. Okay, we have that asymptote. So it will never equal 0. So we're not going to get a root from this. So what's our only answer?
-1.
Yeah, -1. So we're going to have one potential relative extrema. We have one critical number. We need to double check to see if this is a max, a min, or a plateau. So how do we test for that again?
First derivative test or second derivative test?
Yeah, first or second derivative test. So let's do first derivative test. So I make my number line f prime f. All right, so if I have something below -1, am I going to have a positive or negative derivative? It's negative. E to the x is always positive. So 1 minus 2, for example, is going to be negative. So I know my function is decreasing. So I know now that -1 is either going to give me a min or a plateau point. So if we try now zeros on the other side of -1, e to the 0 is 1. 1 plus 0 is 1. That's going to be positive. Okay? So, if you happen to be looking at your notes, okay, we can tell by the first derivative test, it does correspond to a relative minimum. Okay? That's our first derivative test that we were doing there. Okay? Questions? So that stuff still applies. And see how knowing your function, your e to the x, and those properties is helpful in helping you find zeros and things like that. We can disregard e to the x because we know it's never going to hit 0. Okay? Here's kind of an interesting one, the bell curve. Okay? Or the Gaussian model, if you want. It's a bell curve. When you have, in statistics, the normal distribution. Okay? You have what's called a normal probability density function, or the Gaussian model. If you remember that from pre-calculus, we looked at that briefly. We want to show that there are points of inflection when x is plus or minus 1. So if we're trying to show points of inflection, what should immediately come to mind?
Second derivative.
Second derivative, okay? We need to find that second derivative and set it equal to 0.
0.
Okay? Hey guys, as we're going throughout the year here, these are things that should be coming back, should stick in our head. You know, when you hear a specific term, like points of inflection, certain things should automatically come to mind, like second derivative equals 0. When you hear max and min points, you should automatically think first derivative equals 0, points, critical points, things like that. Okay? First derivative test, second derivative test. Try to start making those connections if you haven't already. So now we just need to actually find the second derivative here. Okay, so obviously we have to find the first derivative first. Okay, well we have a constant 1 over radical 2 pi times, what's the derivative of e to the negative x squared over 2? We put down the same thing, e to the negative x squared over 2 times what? What, Peter? Negative x. Yeah, it's going to be a negative 2x over 2. So that's times a negative x. Okay? So that's our first derivative.
Oh my god, the first derivative.
How are we going to find the second derivative?
Taking the derivative of that derivative.
Okay. So we've got that constant. I'm going to leave that hanging out in front here. How do I find the derivative of e to the negative x squared over 2 times negative x? Product rule. Okay. And you know what? I'm going to pull that negative out in front here too. So it's just e to the negative x squared over 2 times x. Then we don't have to mess around with the negative there. Okay, so product rule, the derivative of the first term, so that's the e to the negative x squared over 2, so that's e to the negative x squared over 2, times, it's still a negative x, okay,
Oh my god.
times, that's the derivative of the first part, times the second, but we already took that negative out, so it's just x. Okay, I pulled that negative out there. Okay, plus the first term, e to the negative x squared over 2, times the derivative of the second, which is just 1. Okay?
Why do we times x instead of negative x?
I took this negative here. See that? I made that a positive and I pulled the negative out to be with the constant, just so I didn't have to mess with it.
Okay.
It wouldn't make any difference in your final answer.
And now we set that all equal to 0.
Now we have to set all this equal to 0. Okay? Now, the nice thing is, if this equals 0, okay, then the constant really doesn't matter at all. And just what's inside the parentheses is what we're going to look at. So if you look at what's in the parentheses, I have a negative x squared, okay, it has this e to the negative x squared over 2 in common, so I'm going to factor that out. E to the negative x squared over 2. And then left in the parentheses is going to be a negative x squared and a plus 1. Okay? When does e to a power equal 0?
Never.
Never. So, x equals plus or minus 1. Okay? Hey, you could even say, since this was a show problem, you could say e to the x squared over 2 does not equal 0. So x is plus or minus 1. Okay? So we have now shown, okay, we've now shown the work for it, but any of these show problems, make sure you make a final statement, okay? Alright, so you should then say something like, therefore, since f double prime of x equals 0, when x equals plus or minus 1, there are points of inflection.
Instead of therefore, it should be there 3 because there's 3 dots.
Okay. You could also prove it even further by showing a sign diagram for the second derivative to show that concavity changes. Okay? So negative 1 and 1 are second derivative. If I plug in, say, a negative 2, I know e to a power is always positive. Okay? So if I plug in a negative 2, negative times 4 is negative 4 plus 1 would be negative, which means I'm concave down. If I plugged in something like 0, I would have a positive value, which means I'm concave up. And if I were to plug in 2, again, my second derivative would be negative, so it would be concave down. So since f double prime equals 0 and concavity changes, we know for sure it's a point of inflection. Okay? Alright, so again, there's another application. Now that we know how to do derivatives with exponential functions, that's another application that we can do just with a new type of function. Okay? One last thing here, okay, is finding rates of change. Alright, so MDs in the United States. The number Y of medical doctors in thousands in the United States from 1980 through 1997 can be modeled by the exponential function y equals 475,520 times e to the negative, or e to the 0.027 t, where t equals 0 represents 1980. Okay? That's a 0.0271 t.
That's so close.
Got crammed a little bit here. So that's a t, that's a 1. Okay?
Wait, what? It's 0.0271.
It's 0.0271 t. Yeah, the 1 and the t kind of got crammed together a little bit there. Okay? So now it says, at what rate was the number of MDs changing in 1992? So at what rate, when you see rate, you're thinking? Derivative. Okay. And in 1992, that means t equals what? 12. All right. 0 was in 1980, the year before I was born. Okay. And 92 would be t equals 12.
8 years before I was born.
8 years before you were born. 8 years before I graduated high school, too.
So the year I was born, the year you graduated high school?
Yeah.
So after Little's muchacho.
So, we need a derivative, okay?
Yes, we do.
So, what is dy dx?
The derivative.
Since we were given it in terms of y. What's our derivative here?
0.0271 multiplied by whatever this number is, multiplied by e to the power of this small number, 0 point whatever.
Okay. E to the 0.0271 t. All right, so the constant just stays there. The derivative of e to a power is e to that power times the derivative of the power. So the derivative, that's just a linear function up there.
Wouldn't it be dy dt, not dy dx?
Oh yeah, it is dy dt. Thanks. All right, so yeah, so we have that. We can figure out what that is. At this point, this is one where you do want to use your calculator. It doesn't make sense to have, E in your answer when you're talking about a rate of change for doctors, okay? So when t equals 12, y or dy dt equals 0.0271 times 475,520 times e to the 0.0271 times 12 power. And that should give us 17,839.005 or 0.006 if you round it. Okay? Now, how many, now, what does this mean? What's our unit of measure here for our rate?
What's our
dy. What is y?
Is the number of doctors?
The thousands of doctors, right?
Mm-hmm. Oh,
So it's that many thousands of doctors of MDs, we'll say, per, yeah, the dt, the bottom, tells us what it's per. It's per time. Time in this case is in years. So that's how many per year. Okay? All right, so again, there's another application of derivative we can now do with an exponential model.